Let me show you how to be a good Bayesian. Change your predictions after taking information in.
Actually, can you discuss the role of variational inference here in RxInfer and maybe any innovations that you've incorporated in this area?
The role I kind of touched upon it a little bit is that it acts as like a slider in the controlling the complexity and the accuracy of your inference result. This is the main role. Of course, for some applications, this might be undesirable. For some applications, you may want to have a perfect posterior estimation. But for some applications, it's not a very big deal. We are talking about different needs for different applications here. And the innovation that RxInfer brings, I think it's like one of the few implementation as message passing, like variational inference as message passing, because it's usually implemented as like black box method. That takes a function like a probabilistic model function and maybe does some automatic differentiation or some extra sampling under the hood. And message passing by itself has a very long history, but I think people mistakenly think that it's quite limited to like some product algorithm. But actually variational inference can also be implemented as message passing. And it's quite good. So it opens the applicability of the message passing algorithms. And also, as we already talked a little bit about this reactive nature of the inference procedure. So it's also maybe even the first reactive variational inference engine, which is designed to work with infinite data streams. So it continuously updates these posteriors, continuously does minimization. It does not stop. And as soon as new data arrive, we basically update our posteriors. But in between these data windows, we can spend more computational resources to find better approximation for the variational inference. But all other solutions, let's say that are also variational inference, they basically require you to wait for the data, then feed to the data, or wait for the entire data set, feed the data set, and then you have the result, then you analyze the result, and then you repeat. So RxInfer works a bit differently in that regard.
Mm-hmm. Yeah, fascinating. And that, I'm guessing you have some examples of that up on the RxInfer website. Maybe we can link to that in the show notes for people who are interested to see how you would apply that in practice.
RxInfer currently, I know that it is being used, like for example, to teach students in Eindhoven University for fundamentals of Bayesian statistics. So it does not really require reactivity, but because it's kind of like easy to use and fast, students can do some homework for signal processing applications. What I've already mentioned is that we work with audio signals and with control applications. I don't really have a particular example if RxInfer is being used in the field or by an industry. So it's primarily our research tool currently, but we want to extend it. So it's still a bit more difficult to use than Turing, let's say, Turing, which is also written in Giuliano, because message passing is a bit maybe more difficult to use, and it is not that universal as HMC and NUTS. It still requires some approximation methods. So we still use it as a research tool currently, but we have some ideas in the lab how to expand the available set of probabilistic models we can run an inference on. And yes, indeed, on our documentation, we have quite a lot of examples where we can use. But these examples, they are, I would say, educational in most of the cases, at least in the documentation. So we are at this stage where we have a lot of ideas how we can improve the inference, how we make it faster, such that we can actually apply it for real tasks, for real drones, for real robots, to make a real speech denoise or something similar.
Definitely, that would be super interesting. I'm guessing for people who are into these and also just want to check out. I've been checking out your website recently to prepare for the episode. Actually, can you now? So you've shared the overview of the theory, how that works, what RxInfer does in that regard. Can you share what you folks are doing with lazy dynamics, how that's related to that, and how does that fit into this ecosystem, let's say?
So yeah, Lazy Dynamics, we created this company to commercialize the research that we do at our lab, to basically find funding to make RxInfer better and ready for industry. Because currently, let's say, RxInfer is a great research tool for our purposes. Industry needs some more properties to the addition that I have already mentioned, right? For example, indeed, the Bayesian inference engine must be extremely robust, right? It does not allow to fail if we really work in the field. And this is not really a research question. It's more about like implementational side, right? It's like good code, good code coverage, like great documentation. And this is what we kind of also want to do with Lazy Dynamics. We want to take this next step and want to create a great product for other companies, such that they can rely on RxInfer maybe in their research or maybe even in the field, right? And maybe we create some sort of a tool set around RxInfer that will allow you to maybe debug the performance of your probabilistic program or your probabilistic inference, right? It's also not about research. It's about like having it more accessible to other people, like finding bugs or mistakes in their model specification, make it easier to use. Or maybe, for example, we could come up with some sort of a library of models, right? So you would want to build some autonomous system, and it may require a model for audio recognition. It may require a model for video recognition. And this kind of set of models, they can be predefined, very well tested, have a great performance, super robust, and basically Lazy Dynamics may provide an access to this kind of a library, right? So, and for this kind of, because this is not a research related questions, it must be done in a company with like very good programmers and very like good code coverage and documentation. But for research purposes, RxInfer is already a great toolbox, and basically many students in our lab, they already use it. But yeah, because we are all sitting in the same room, let's say on the same floor, we can kind of brainstorm, find bugs, fix it on the fly, and they keep working that. But if we want for RxInfer to be used in industry, it really needs to be a professional toolbox with like a professional support.
Yeah, I understand. That makes sense. Surprised you can, I don't know when you sleep though, between the postdoc, the open source project and the company.
Yeah, it's a great comment. It's hard.
Yeah, hopefully we'll get you some sleep in the coming months. To get back to your PhD project, because I found that very interesting. So your dissertation will be in the show notes. But something I was also curious about is that in this PhD project, you explore different trade-offs for Bayesian inference architecture. And you've mentioned that a bit earlier, but I'm really curious about that. So could you elaborate on these trade-offs and why they are significant?
We already touched a little bit about that. So the main trade-offs here are kind of a computational load, efficiency, adaptivity, high power consumption, magic. And another aspect actually, which we didn't talk about yet, is structural model adaptation. So this is the requirements that we are favor in RxInfer. And this is the requirements that were like central to my PhD project. And this all arises, all of these properties, they are not just coming from a vacuum. They are coming from real-time signal processing applications on autonomous systems. We don't have a lot of battery power. We don't have a very powerful CPUs on these autonomous devices, because essentially what we want to do also is that we want to be able to run a very difficult, large probabilistic models on a Raspberry Pi, let's say, right? And Raspberry Pi doesn't even have a GPU. And we can like buy some small sort of a GPU and put it on a Raspberry Pi, but still like the computational capabilities very, very limited on edge devices. And for example, one may say, okay, let's just do everything in the cloud, which is a very valid argument actually, right? But we also, in some situations, the latencies are just too big. And also maybe we don't have access to the internet in some areas. but we still want to like create this adaptive Bayesian inference systems like a drone that they may explore some area, maybe in a mountain or something where we don't really have an internet, so we cannot really process anything in the cloud. So it must work as efficient as possible on a very, very small device that doesn't have a lot of power, doesn't have a lot of battery, and still this should work in real time. Yeah, I think this is mostly the main trades-off. And in terms of how we do it, right, we use this variational inference and we sacrifice accuracy with respect to scalability. Reactive message passing allows us to scale to a very large models because it works on factor graph.
Let me show you how to be a good Bayesian. Change your predictions after taking information in.